Well, thank you for that introduction, Alan, and I really want to thank Brad in particular for giving me this lead-off batter position here in the pit talks. I really appreciate that because, like a really good academic here, I finished this presentation last night sometime, and as the lead-off hitter here, I don't have to hit a home run. I just need to get to first base, right? So I just need to get a single or even a base on balls will work, and the rest of my team here is going to bring us around to score. So I'm hoping this is okay, and if it isn't, it's going to be at least a base on balls here. So I'm here to talk about Geotechs. I actually didn't think they'd pick up this lecture when I put the submittal in, but here I am. I did this meta search to figure out, what our representation of the population is. So about, according to Meta, about 2 to 3% of the workforce of the U.S. are engineers. 20% of those engineers are civil engineers. 10% of those civil engineers are geotechnical engineers, which makes us 0.05% of the workforce, or 0.3% of the U.S. population. I think that number is still high, but that's small. We are a subculture, and like every subculture, we have our own way of looking at the world, we have our own language, we have our own proclivities, and it's nothing wrong with that, but it does make us weird. And in case you don't think that's true, how many people here are not geotechnical engineers associated? I know there's some geologists here. Come on, raise your hands. You're not geotechnical engineers, all right? Now tell me the truth. Are we weird? Yeah, I see a lot of head nodding out there. All right, so just to let you all know, the rest of the world thinks we're weird. Sometimes we're good weird, sometimes we're bad weird, but whatever we are, we're geotechnical weird. So that's what I'm here to talk to you about. The first part of my presentation is the Inigo Montoya presentation. This is about language and how about we don't really communicate even though we're using the same words. I really appreciate being set up by a geologist because this is a geology example. This is one we're all familiar with here. On your left, we see a soil there that's definitely a gravel, lots of particle sizes. We would, as geotechnical engineers, call that well-graded because that's good stuff, right? There's lots of different gradation. On the right, we have a very uniform sand. That's the bad stuff, so it's poorly graded. Unless you're a geologist, then the stuff on the left is well sorted because they're looking at the process and not the product. And the other one is poorly sorted. Well, this is the case where a common language, using the same words, doesn't mean the same thing. We know the positive adjective there belongs with the stuff on the left. It's well graded. The other stuff's poorly graded. Sorry, geologists, you're wrong. We're right. We are the geotechnical engineers. Case closed. My next one is, I call the let's get our ASCE together system here. Don't you guys love those illustrations by John Maggard that Hayward Baker used to do, and now we can't get the catalogs anymore? Anyway, so this is about how we define our world. Everybody else in the world would define, they're looking at ASCE system. Any other engineer said, hey, Y is up, Z is up, of course. No. In a geotechnical world, Z is down. Why? Because the good stuff is under the ground. Positive Z down. Clearly, again, we are right. The rest of the engineering world is wrong. Am I right, Sebastian? Yeah, I'm right. Okay. Oh, we do have one thing, another group we have this in common with us, though. That's the submariners in the world, right? They live under the water. They also like depth, Z positive down. So here's a case where we have at least one other very, very, very sub-minority group of people in the world that agree with us. So that's nice to have. My next example, I call it, let's not get stressed out. This is my favorite example of all. This is where we really excel because geotechs don't do tension. Tension is bad for you. It raises your blood pressure. It shortens your life. It makes your relationships with your friends worse. Tension is bad. We ban more circles on the left side of the y-axis in our business. That's wrong. For geotechs, compression is positive. Compression is good for you. What do you do with your hyperactive dog? You put that heavy blanket around them, right? It compresses them. It warms their soul. It calms them down. We have this totally right. I don't know what's wrong with our structural friends and our engineering mechanics friends that have defined, compression as negative. Compression is clearly positive. Tension's bad. We don't do tension as geotechs. Okay, now we get to our proclivities that are starting to get a little dicey here. So this is our skating on thin ice. My first part is the relatively speaking. You know, this is our favorite diagram in geotechnical engineering, at least in introductory soil mechanics classes. This is where we talk about the constituencies and what percent of soils are made up of different parts. And so we should be talking about what percentage of soil is something. So let's talk about the voids. Right, how much of my soil is voids? Well, clearly the way to define that, you take the amount of voids, the volume of voids, and you divide it by the total volume, of course, and that tells you what percent of your soil is voids. But we like to use this really weird thing called the void ratio. We're going to take the total amount of voids. We're not going to, the volume of voids, we're not going to divide by the total volume. We're going to divide by something less than the total volume, the volume of solids. This is really weird. You know, if we did this with your gas tank, and we told you your gas, you know, when your gas tank was half full, if we divide the air fuel ratio, it would have a value of 1. I mean, this makes no sense. It has an infinite top to this. And then there's the water content. We want to talk about the water. How much water is in there? Well, we take the volume of water divided by the total volume. Volumetric water content makes perfect sense. Our agronomists and soil scientist friends do this all the time. What do? We don't even use the volume, we use the weight, which is really weird because the specific gravity of water is 1 and the solids are 2.6. But again, we're taking what we're interested in and we're not even dividing by the total volume. It's weird. My students just did their Atterberg-Limbus test on bentonite. They got a 200% water content for the liquid limit. I said, great. And they said, what does that mean? It's 85%. It's a volumetric water content of 85%. That makes sense. 200%, they don't know what it means. Okay, now for the part where we've definitely gone way, way, way too far. This is about unhealthy relationships that we geotechnical engineers have, and I'm talking about our stress-strain relationships. This is one of the most bizarre things in the world. How does the rest of the world talk about stress-strain relationships? Well, they talk about the stress as a function of the strain. Here's the stress-strain curve for a very typical elastoplastic soil or material. Right? You see an elastic portion, you see yielding, you see strain hardening, and then you see the plastic modulus. How do we do it? Okay, well, first of all, we like to plot strain as a function of stress. Okay, I can deal with that. That's just an inverse. But then we use this log scale, which is not only bizarre, it's really distortive. And we have to go through a lot of machinations to do this, right? So here's our traditional stress-strain curve that the rest of the engineering world uses. First, we like to have to flip it on its side so we can plot strain versus stress instead of stress versus strain. Then we have to turn it upside down so that positive compression is down. That's okay because we've already decided that positive C is down, so that's all right. But then we do this really, really weird thing where we then take the log of the stress and it totally distorts the curve. That one on the lower right looks nothing like the one on the upper left. And the parts that are linear, they're not even linear anymore. And just to drive this home, this is a real stress-strain curve from a residual soil in Auckland, and you can find lots of soils that behave this way. But you look at that, and if I was to do a Casa Grande construction on that and find the pre-consolidation stress on it, if you look at that, you can look in there, it's going to be someplace between 400 and 500 kPa, right? So what do we tell our students? Well, that's the stress that soil was loaded to sometime in its geologic history, and now it's less than that. And when we get to that point, suddenly the modulus of the soil is going to change, and it's going to behave very differently when we get the pre-consolidation stress. This is what that soil looks like in a traditional linear stress-strain curve. That looks pretty much like an elastic soil unloading, with plastic deformation on the end. There's no evidence whatsoever of a pre-consolidation stress. That's like a fiction, right? I think this is one of our biggest sins. I think we could get rid of this one. It's just very deceiving. And we've gone way too far with this. And actually, if you look back at the earliest publications in geotechnical engineering, you find that they didn't always plot these stress-strain curves as the log of stress. There are plenty of linear presentations of that. They're still using void ratio for the deformation part, though, which is still kind of weird. Anyway, I hope you enjoyed this presentation. We truly are weird. We are this subculture. We should celebrate that. We should feel the teal. Yes, feel the teal. But make sure you know, when we're doing it the right way, where we're clearly wrong, the rest of the world is wrong, and when we're doing it the wrong way, but it's whatever we're doing, it's always the geotech way. Thank you very much.